Welcome to the next video on logarithms. So far we've discovered that we have got a way of writing out repeated multiplication using exponential notation, and that powers represent repeated multiplication. When we multiply numbers together, we simply add the exponents. When we divide numbers, we subtract the exponents. Adding exponents only works when you have the same number base. Subtracting exponents only works when you have the same number base. A number raised to the power of 0 is 1. The rules really don't apply if the number base is 0, as 0 to the power of 0 is a bit meaningless, as is 1 over 0. And finally, we've discovered that numbers can be raised to fractional powers. So in the last video we found that 2 to the power of a half equals the square root of 2. We're going to use fractional powers in a little while, but first of all we're going to do some much more simple calculations, and we're going to use base 10. 10 times 100 equals 1000. We can easily see that 10 can be written as 10 to the power of 1, and that 100 can be written as 10 to the power of 2, 10 times 10, and the result can be written as 10 to the power of 1 plus 2, which is 10 to the power of 3, which is 10 times itself 3 times. We'll now do that calculation using log tables, and the way log tables are laid out is like this. On one side we're going to have our number, in this case it will be 10, 100 and 1000. On this side we're going to have a number that we're going to call the logarithm. The logarithm is simply the power. So in this case the logarithm of 10 is the number 1. Here the logarithm of 100 is 2. And here the logarithm of 1000 is 1 plus 2, which is 3. So we look up our first number, which will be 10. We'll find the logarithm, write it down. We'll look up our second number, which will be 100, find the logarithm, write it down. We add those numbers together, find that total, and then do a reverse lookup and say that 10 to the power of this number here is the answer. Here's our table of logarithms. On this side we have the number, which is 10, 100, 1000. Here we have 10 to the power of 0, which we know is 1, 10 to the power of 1, 10 to the power of 2, and we're going to call that the logarithm. This column here just indicates, rather crudely, 10 to the power of 0, 10 to the 1, and so you can see on this side these numbers here, 10 to the 1, 10 to the 2, 10 to the 3. Our first number is 10. The logarithm is 1. So we write down the logarithm 1. The next number we want to multiply is 100. The logarithm is 2, so we write it down. The result of that is the number 3. So we go down the logarithms and find the number 3 and do a reverse lookup. 10 to the power of 3 is our result, which is 1000, which is this calculation here. 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. Of course, we don't have to use the number 10. We can use the number e, which is approximately 2.718, which is a much beloved number for mathematicians. We'll do a similar kind of calculation. Here we'll use 2.718 multiplied by 20.063. So again our number is 2.718, the log is 1. Our next number is 20.086, and the logarithm of that is 3. So what we're saying is that e to the power of 1 is 2.718, e cubed is 20.086. We add the numbers together and we find that the result of that is 4. So we go down our table of logarithms, find 4, and we get the result 54.598, which is 2.718 multiplied by 20.086. If we now write down the calculation that we've just done, we worked out that e to the power of 1 times e to the power of 3 gave e to the power of 1 plus 3, which is obviously e to the power of 4. And e to the power of 1 was 2.718, and that was multiplied by e cubed, which was 20.086, and that gave the result of e to the power of 4, which was 54.598. Whilst these are practical calculations, on one level they're not very useful. It's not often in life we're going to want to multiply together a number as specific as this with a number as specific as this. We want to multiply any number we can think of. In fact, specifically, we want to be able to do a really simple calculation. What is 2 times 3? And so far, using powers and logarithms, we haven't been able to do that. But now that we have fractional powers, or in this case, fractional logarithms, we can do that. So we'll make it nice and easy. 10 is a familiar number. We'll use numbers to the base 10 because it's easy to understand. And instead of having whole number logarithms, 10 to the power of 1, 10 to the power of 2, we can choose a fractional logarithm. Let's try 0.1. The numbers perhaps aren't that useful, but we can see here we've got a number that's almost 2, and we've got a number that's a bit above 3. But of course, we can always make these numbers closer and closer together. And now we've got something that's almost useful. We have to go down quite a long way, but we find that 2 is approximately 10 to the power of 0.3. And we keep going down, we find the number 3 in this column, and we find that 3 is approximately 0.48, and the result of that in this column will be 0.78. And when we look up 0.78 and get the result, we find that is just a little bit above 6, which is pretty close to 2 times 3. Of course, we can make this ever more precise simply by adding more zeros, but it does become rather long-winded looking up all of these numbers, because the more numbers I add, the further down the table we have to go in order to find the number that we're looking for. So instead, we'll use a sort of a cheat sheet. We'll pretend that all the numbers on this side represent every number we can possibly think of, and that we have looked up the logarithm on this side. So we'll put in the number 2 on here and find that the logarithm is approximately 0.301. Then we'll look up the number 3, and we find that the logarithm is 0.477. and therefore the result is going to be 10 to the power of 0.301 plus 0.477, which is going to be this number here, 0.778, and 10 to the power of 0.778 is 6. And that's how log tables get used. We're now going to do exactly the same calculation, except we're going to use what are called natural logs, using the number 2.71828, otherwise known as Euler's constant. And the calculation is identical, it's just the fine detail of the numbers that changes. So now we look up the number 2 and find the logarithm, and we find that e to the power of 0.693 is 2. We look up the number 3 and we find that e to the power of 1.098 is 3. We add these logarithms together and we find that e to the power of 1.792 approximately is 6. So we write those out and we find e to the power of 0.693 multiplied by e to the power of 1.098 gives e to the power of 1.792. And this simply equals 2 times 3 equals 6. And of course we can now choose almost any number we want. We go back to the first video where we had the observation that in the days before calculators, working out a calculation with a lot of decimals in it will be extremely difficult to do. When you have log tables, this complex calculation just becomes look up the logarithm, add them together, look up the anti-log, as it's sometimes called, and there's your answer to that times that. The final video in this series will cover what you will probably get given in lessons on logarithms, and you get introduced to the following rather strange and probably incomprehensible observation that the log of a to the power of x equals x log a. And you may well be wondering how on earth we're going to go from numerical calculations such as these to an apparently abstract piece of algebra like this. Actually, we've almost done that calculation already. Watch the next video to find out how.